Welcome back to AI Papers, a deep dive. No press releases, no secondhand summaries, just the paper itself and the honest critique. All right, let's dig in.
A new hire walks into an office on their first day. No documentation, no handover notes, nobody with time to explain how anything actually works. One version of that hire solves whatever lands on their desk, goes home, and wakes up the next morning having forgotten all of it. Every quirk, every workaround, gone. The other version keeps a running cheat sheet. The printer on the third floor jams if you feed it more than 20 pages. Dana approves the budgets. The VPN still wants last year's password. Same person, same raw ability, but week 4 is dramatically smoother than week 1, purely because of the notes. The paper I want to dig into asks whether you can train that second instinct directly into a language model. Not be good at today's task, but be good at writing yourself the cheat sheet that makes tomorrow's task easier. And the real bet, the thing that makes this more than a clever trick, is whether that note-taking habit transfers to a job the model has never seen before. The paper is called Connect the Dots: Training LLMs for Long-Lifecycle Agents with Cross-Domain Generalization via Reinforcement Learning. It went up on archive on June 18, 2026, and we're recording one day later. Quick note before we go any further, this episode is AI-generated. The script was written by Anthropic's Claude Opus 4.8, and the two voices you're hearing, well, I'm Bella.
And I'm Finn. We're both AI voices from 11 Labs, and the show has no affiliation with Anthropic or 11 Labs. And that transfer to a job it's never seen line, Bella, that's exactly where today's agents fall apart. Because right now, frontier models have a very specific kind of amnesia. You can drop one into an environment, hand it a task, and it'll reason its way to something good. But the instant you give it the next task, it starts from zero. Everything it figured out about that environment the first time around just evaporates, unless some human engineer has hand-built scaffolding around it. Memory banks, retrieval systems, prompt hacks. The authors are blunt about it. These agents get lost in environments that aren't fully specified. They act on wrong assumptions with way too much confidence, and they lose the thread after a few rounds of interaction.
And the deeper point is that this isn't a bug in any one model. It's baked into how we train them. The reinforcement learning that made the reasoning models good, the O1s and DeepSeek R1s of the world, it all optimizes for one thing: solve this task from scratch as well as you can, which is great if your tasks arrive in isolation.
But that's not the future people are actually building toward. The vision is an assistant that knows you better after 6 months, a coding agent that maintains a repository for weeks, like a real engineer who's been on the project a while.
Right. And for those agents, solve every task from scratch isn't just suboptimal, it's optimizing for the wrong thing entirely. So the question the authors pose is, can you train a model end-to-end with reinforcement learning to have a meta skill? Not be good at this specific game, but be good at getting better at whatever environment you're dropped into. Explore it, take notes, exploit those notes. And does that habit generalize?
So let me make sure I've got the one-sentence version, because the framework has a few moving parts that sound alike.
The one sentence is this: instead of training a model to solve each task fresh, you train it across a whole sequence of related tasks to explore the environment, write itself useful notes between tasks, and solve the later tasks by reading those notes. And the claim is that this learn-to-learn habit then shows up in brand new environments. And the cleanest way to feel why any of this is necessary is the environment they built to force it. They call it FrozenLake-Obscure. Classic Frozen Lake is a little grid. You navigate to a goal, avoid the holes, you move up, down, left, right. Simple. Their twist is wicked. The action buttons are now just labeled A, B, C, D, and the mapping from those labels to actual directions is randomly shuffled and hidden every time you get a new map.
So on a fresh map, you literally cannot know which button moves you which way.
You cannot. And that creates a hard information-theoretic wall. Their own illustration is great. Imagine your starting square is surrounded by 3 holes. With no idea what the buttons do, you fall in on your very first press about 3 times out of 4. 75% dead on step 1, and no amount of cleverness saves you, because the information just isn't there.
Which is the whole design philosophy, right? They needed an environment where solving from scratch hits a ceiling, because if a task is fully solvable cold, the model has zero incentive to take notes. The training would just collapse back into ordinary reinforcement learning.
Exactly, Finn. The only way to do well at FrozenLake-Obscure is to spend your early tasks figuring out the hidden mapping and writing it down so your later tasks can use the cheat sheet. The note-taking isn't a nice-to-have, it's the only path through the wall.
Okay, so this is where the terminology gets genuinely confusing, and I think it's worth slowing down. Because the paper has 3 things that sound nearly identical, and the whole episode depends on holding them apart. There's standard task-by-task RL, there's something they call CoD-Deploy, and there's CoD-Train.
Let me take the framing they use because it's clean. Think of it as climbing one rung up a ladder. The unit of a reinforcement learning attempt in language models has been creeping upward for years. First, it was a sequence of tokens, one answer to one prompt. That's your basic reasoning RL. Then it became a sequence of turns, a multi-step agent doing one task. This paper takes it one more rung, a sequence of tasks, a whole life cycle in one environment. So, CoD-Deploy is what happens at test time. The agent faces task 1, solves it while poking around, then runs what they call an update context episode. It stops and condenses what it just learned into a hint. Then it faces task 2 with that hint pasted into its prompt, solves it, updates the hint again, faces task 3, and so on. It's online learning by trial and error, except nothing about the model itself changes, only the note it's carrying.
Hold on. When you say it learns during deployment, is the model retraining itself between tasks, tweaking its own weights on the fly?
No, and that gap is the entire trick, so I'm glad you pushed on it. At deployment, the weights are frozen solid. The model is not getting one neuron smarter. The only thing that changes from task 1 to task 4 is the paragraph of text it wrote for itself and stuck in its own prompt. It's the difference between growing new instincts over years versus jotting a reminder on your hand before you walk into a meeting. The hand note is in-context learning. The model's actual capability never moves.
So then where does the training come in?
That's CoD-Train. Same loop, exact same interleaved shape. Solve a task, write a note, solve, write. But now you run many of these sequences in parallel, and you do update the weights. You're not teaching it Frozen Lake, you're teaching it to be good at the loop itself, good at solving, and good at note writing.
And there's one quietly elegant thing about that loop that makes the whole project tractable, which I want to flag because it's easy to skate past. Every task in the sequence hands back a reward. Did you solve it or not? So the number of reward signals grows right alongside the number of tasks. The reward density stays constant no matter how long the life cycle gets. You're never stuck trying to assign credit across some enormous span with one lonely signal at the very end.
Which is a perfect handoff to the genuinely hard part, because credit assignment is where this paper actually lives. Finn, this is your corner.
It is the oldest headache in all of reinforcement learning. If a reward only shows up at the end of a long chain of actions, how do you figure out which earlier move actually earned it? The chess version. A move on turn 3 is what wins you the game on turn 40, but the only thing you're told is, you won. How do you reward turn 3? The standard answer goes all the way back to Bellman in the 50s. It's called rewards to go. You don't judge a move by what happened immediately after it. You judge it by the sum of all the good that flowed from it downstream. And the soccer version makes it click. You're reviewing game film, deciding who to praise. The naive method credits only the player who scored. The smart method credits the defender whose interception in minute 10 set up that goal in minute 40.
And in this setting, the interception is a good note.
That's the whole move. An update context episode early in the sequence, a note the model wrote at task 1, gets judged by how well tasks 2, 3, and 4 went. If the note was good, those downstream tasks went well, and the note gets a big positive credit. Write a bad note, your future self flails, the note gets penalized. That's how you reinforce good note-taking, even though the payoff is several tasks away. Now, the method they build this on is GRPO. That's the critic-free approach from the DeepSeek math folks. One-line reminder, instead of training a separate model to estimate how good a situation is, GRPO just runs the same scenario many times in parallel and uses the group average as its yardstick. It's grading on a curve against 20 copies of yourself attempting the identical thing. Did this run beat the average of all the others?
But vanilla GRPO assumes one reward per attempt, and here you've got a whole sequence of them.
Right, so their adaptation is to ask that beat the average question at every position in the sequence. Lay all the parallel timelines side by side, and at each point ask, of all the ways this run could have gone, did this one do better than typical right here? And the contrast with the obvious alternative is, honestly, the cleanest justification in the whole paper. A prior approach, a system called Orbit, just sums every reward across the whole sequence into one lumped final number.
Which sounds simpler.
It's simpler, and it's hopeless. With one lumped reward, you can't tell which episode deserves credit, and the signal gets more and more diluted the longer your sequence runs. The authors report that on FrozenLake-Obscure, that coarse approach simply was not feasible for effective training. Their fine-grained, per-episode version worked across the board. That head-to-head is the argument for the entire design.
So let's actually land the result this all builds toward, because when I first read it, I had to reread it. They train this on FrozenLake-Obscure, starting from an 8 billion parameter Quen model, sequences of 4 tasks, and they track 2 numbers as training goes on. The first number is from-scratch performance. Task 1, cold, no notes. Over the course of training, that creeps from around 18% up to maybe 45%. A real improvement, but it slams into that information theoretic wall we talked about. You cannot reason your way past hidden buttons.
And the second number?
The second number is performance on the 4th task in the sequence, armed with the notes the agent wrote itself across the first 3. That one goes from 28% to 76%, from under a third to over 3/4.
And the gap between those two numbers is the whole paper.
It really is. Because look at what it's telling you. The cold start skill barely moves. The model is not getting meaningfully smarter at Frozen Lake. But the with notes skill nearly triples. The model isn't getting better at the task. It's getting better at helping its future self. It's the open notes exam. Your cold open score stays flat, but your score on the 4th exam, where you're allowed to consult the notes you took during the first 3, climbs through the roof.
And the notes themselves are the part that genuinely got me, because context updates sound so abstract until you see what the model actually wrote.
Oh, the appendix is gold. The Frozen Lake hint the agent wrote for itself reads almost literally, Direction 1 equals right, Direction 2 equals up, Direction 3 equals down, Direction 4 equals left. It reverse-engineered the hidden mapping through trial and error and left itself a cheat sheet in plain English.
Which is the thing that separates this from its closest ancestor, and I think it's the most beautiful framing in the paper. This learn-to-learn idea isn't new. There's a line of work from around 2016, the RL-squared stuff, where you'd stitch several episodes into one long trajectory so the agent learns from its early experience. But in that older work, the thing carried between episodes was a neural network's internal hidden state. Fixed size, opaque, nothing a human could ever read.
And here, the hidden state is a paragraph you can read.
That's it exactly. Fixed compute becomes adaptive compute. The note grows or shrinks as needed. And it's human-readable. You can look over the agent's shoulder and watch it figure out the world. In the alchemy environment they tested, the note becomes a running recipe book. These ingredients combine into that, these don't. In a terminal command environment, it distills a reusable pattern. Copy with one command, extract with another, change directory first. Same instinct, totally different domains.
And that's the bridge to the claim everything's been building toward. And Finn, I suspect this is where you start getting uncomfortable.
You know me too well. Because the headline of the paper is Cross-Domain Generalization. The story is, we trained this note-taking habit on toy grid games, and it showed up in environments the model never trained on. And I want to be careful here because the authors are genuinely honest about this. I'm steel-manning their own footnotes, not catching them at anything. Here's the asterisk. The clean version of the claim would be, the connect the dots skill transferred across different tasks in a new domain. But on that terminal command simulator, when they ran the proper setup, a sequence of different tasks, the later tasks showed no gain over the earlier ones. None. Because the terminal tasks within a sequence just weren't related to each other. There were no dots to connect.
So, where did the improvement come from?
It only appeared in what they call the Ralph loop setting. And that's worth a quick gloss. The Ralph loop, named after a blog post, is just an agent attacking the same identical task over and over to iteratively improve. The authors frame it as a special case of their framework where every task in the sequence happens to be the same task. And the cross-domain gain only showed up there.
So it's less the general note-taking habit transferred to a new job,
And more, the agent got better at one task by retrying it and reflecting between attempts. Which is a real and useful thing, but it's a within-task reflection benefit, not the connect the dots across different tasks story the abstract's confident phrasing implies. And the authors flat out say they can't pinpoint the root cause of that terminal improvement. They footnote it as needing more investigation.
I think that's the fair reading, and it's worth sitting with rather than waving away. Let me add the other critique that I think a careful listener should hold, which is that some of the headline result might be tautological by construction.
Say more.
Well, they engineered FrozenLake-Obscure specifically so that from-scratch solving is capped by hidden information. That guarantees a big gap between the cold task and the later note-armed tasks. But that gap is the headline number. The design ensures the result exists. It doesn't, on its own, prove the model learned a general skill versus learning to exploit one particular structure the environment was built to reward.
Although, in fairness to them, the fact that the cold start number does improve at all, even capped, suggests something real is being learned about exploration, not just exploitation of the rigging.
That's fair. I'd call it suggestive, not settled. And then there's the scale honesty, which the authors own completely. This is one 8 billion parameter model. Sequences of length 4 evaluated out to 8. The entire context is a single paragraph of text appended to the prompt. No persistent memory bank, no skill files, none of the richer machinery you'd actually want. They explicitly flag all of that as future work.
And the algorithm itself is admittedly held together with tape in places. The stability fix, the thing that keeps training from going off the rails, is a hand-tuned reweighting heuristic they introduced after watching their first approach go unstable. On the mixed domain training setup, they saw real instability and some performance degradation. They literally call for a more principled, theoretically grounded algorithm in future work. The method works empirically, it's not on firm theoretical footing.
There's also no strong external baseline, which I think is the cleanest methodological gap. Everything is internal. Their algorithm versus vanilla GRPO versus the unstable variant, all on their own custom environments. The other meta-learning for LLM systems get discussed and differentiated in prose, but nobody's run head-to-head on the same tasks. So the relative strength of this approach is more asserted than measured.
All of which makes this firmly a proof of concept paper, and the authors say exactly that. The word they use is potential. Demonstrates the potential for out-of-distribution generalization, not here is a deployed capability.
And yet, I don't want the critique to bury what's genuinely surprising here, because there's a real buried in all the caveats. A habit learned on shuffled button grid games leaked into terminal commands at all. Even granting Finn's asterisk that it's mostly within task reflection, something about the operational loop of explore, record, exploit, survived the jump between wildly different domains. That's the live wire.
I'll grant you that. Something transferred. I'm just not convinced it's the thing the title says transferred.
And that's the honest place to leave it. Let me zoom out to why this reframing matters even at proof of concept stage, because I think the conceptual move outlasts the specific experiments. The authors borrow a framing from Cholet, fluid versus crystallized intelligence. Crystallized is your accumulated, baked-in knowledge. Fluid is your ability to adapt to something novel on the fly. Standard task-by-task RL builds crystallized skill. This is an attempt to train the fluid part, and the pitch is they're complementary, not competing.
And it slots into a bigger shift in what the field even wants from agents. There's this idea from Silver and Sutton last year, the era of experience. Agents that learn from their own experience at test time rather than only from a frozen training set. This paper is one concrete data point on that vision. The operational loop of figuring out an environment might be something you can bake into the weights, instead of something a human engineer has to bolt on with external memory systems for every single new deployment.
Which is the practical payoff if it scales. Today, every long-lived agent deployment needs its own bespoke scaffolding, and the agents still get lost. The promise here is that the model brings its own note-taking instinct to the table. You stop needing armies of engineers building memory pipelines around every new agent.
And there's a genuinely intriguing detail tucked in the data side. These synthetic environments give you essentially infinite training data. 50,000 instances per environment, and you could generate far more. The dream they gesture at is train on infinite toy data and hope the meta-skill transfers to the messy real world.
Which is exactly the thing we don't yet know holds. But as a direction, it's alive, and they released the code to chase it.
That feels like the honest summary. The mechanism is clever. The credit assignment trick is the real contribution, and the central result, that the model isn't getting smarter at the task, it's getting smarter at helping its future self, is a genuinely sharp idea, cleanly demonstrated.
With the reservation you keep coming back to, which I think survives the episode intact.
It does. I take the point that something transferred across domains. I'm just not sure the experiments isolate the connect the dots skill from plain old retry and reflect. And the authors can't fully explain it either. So I'd file the generalization claim under promising and unresolved, not shown. That's not a knock on the work. It's where the work honestly leaves it.
Which is a perfectly good place for a proof of concept to leave you, with the direction proven interesting and the hard version of the question still open. That new hire we started with, the one who learns to keep a cheat sheet, the paper's real claim is just that you can train the habit of keeping the cheat sheet. Whether it survives a move to an entirely different office, that's the next paper.
The show notes have a link to the paper and a few related reads if this one caught you.
And if you want the full transcript with every bit of jargon tappable, plus the concept pages that link this episode to the others we've done, that all lives on paperdive.ai.
This has been AI Papers, a deep dive. Thanks for spending the time with us.